Hi everyone. So in this video, we are going to be talking about Riemann sums. So, and definite integrals. So here we have a curve where f of x is greater than or equal to 0 on the interval from a to b. And let's say we have four rectangles. So let's say, let's split this into equal rectangles. Equal width rectangles, I should say, roughly. So the idea here is that on the interval, in the interval between a to b, if we split it into n equal pieces, and each one has a width, so this right here is the width, right, of the rectangle, and the width is delta x, and we say it's b minus a, minus a divided by n, we can build a rectangle on each piece using the function value at the left end point. So they see how I did this is the left end point, and then left end point, and then I do my my rectangle, left end point, rectangle as the height. So the idea is to add up all the rectangle areas and for us to be able to get an approximation. This is what it's called Riemann sums. So for this particular case, I would say that n is equal to 4 because I have 4 rectangles. The actual formula for Riemann sums says that Rn is equal to the sum from I is equal to 1 all the way to n of f of x sub I delta x, where delta x is equal to b minus a over n, and x sub I is equal to a plus I times delta x. This does seems like quite a bit, but we're going to do an example and work this out. And this is as n goes to infinity, so as the number of rectangles increase, the Riemann sum approximates the actual definite integral from a to b of f of x dx. As you use more and more rectangles, the approximation gets better and better. In the limit, as n goes to infinity, the Riemann sum becomes the exact area under the curve, and that's what the definite integral represents. You will not need to evaluate Riemann sums all the time, or with a lot of rectangles, but on this exam, you may have one that has like n equal to 4, no more than 4 rectangles, just to make sure that you know how to use it. So you do need to understand what they represent and how to be able to interpret them. Alrighty, let's see if we can do one later. Now let's look at the fundamental theorem, and we'll come back and do this on a separate video on actual Riemann sums. I just wanted to introduce it here. So now let's look at the fundamental theorem of calculus, of integral calculus right here. So the fundamental theorem of integration. What this says that when we have an integral from a to b, so we have a specific limit, it's f of x dx, it's equal to f of b minus f of a. Remember that when we do capital letters, that means it's the integral, and where we say that where f is any antiderivative of f. So what we're saying is that f prime of x is equal to f of x, okay? And so to actually do the computation, what this means is that the integral of from a to b on in an interval, so from f of x dx is equal to So we have to integrate. Then we have to evaluate from a to b. So it's f of b minus f of a. This is what it means. Okay. So the bracket notation, this bracket notation right here is just shorthand for saying evaluate f at the top limit, then subtract f at the bottom limit. You'll use this notation every time you compute a definite integral. Two important things to note. First, there's no plus c in a definite integral. The constant cancels out when you subtract f of a from f of b, so you never need to write it. Second, it does not matter which antiderivative you choose, they all give you the same answer. So let's work through a problem. So let's say you have the integral from not a, but from 0 to 4 of 2x plus 1. So when we integrate this, right, this becomes x squared plus x. This is the integral of this. But we then have to evaluate this integral from 0 to 4. How do we do that? We basically have to plug in 4 everywhere we see an x. So we have 4 squared plus 4 minus. Be very careful right here. Make sure you put your parentheses so you don't make a mistake. In this case, it doesn't really make a difference, but we'll just put it there. So 0 squared plus 0, so this becomes 16 plus 4 minus 0. So we have 20 minus 0 is equal to 20. So what we're saying is that the area of this line, which is a straight line between 0 and 4, the area under the line or under the curve of this function right here, 2x plus 1, on the interval between 0 and 4 is equal to 20. Now we can do a quick application, but let me see. So let's say you are looking for the area under the curve. So a lot of the times, area under the curve is represented by AUC, area under the curve. And usually what that does in terms of applications, it's the total drug exposure over a period of time. So the more drug absorbed, the larger the area under the curve. So if we look at, so let's look at an example where we have C of T is the drug concentration. So we'll say that this is the drug concentration in blood. At time t. Then we want to know what is the area under the curve from 0 to some time t. So, well, what do we need to do? We need to find C of t. We need to find what is this integral right here. So we'll say that the area under the curve is equal to C of t, which is equal to some sort of integral of, so it's antiderivative, of C of t dt. So let's say we have a specific problem and we say that C of t is equal to 5e to the negative 0.3 t. And we want to be able to find the area under the curve from t is equal to 0 to t is equal to 4. So we want to know the total area the total concentration between 0 and 4 hours, or maybe 0 and 4 minutes. So we do the integral from 0 to 4 of 5e to the negative 0.3 t dt. Remember that I like to really write this as the 0.3 as negative 3/10. So when we evaluate this, I like to pull my 5 out, right? So this right here is going to be the reciprocal of 3/10, right? So this is going to be 10 over 3 times e to the negative 0.3 t from 0 to 4. So this equals to negative 50 over 3 e to the negative 0.3 t. But we have to evaluate this from 0 to 4. So when we evaluate this, we plug in t is equal to 4 first, and then minus when t is equal to 0 over 3. And remember that this is just 8 over 0, this is going to be equal to 1. So we have negative 50 over 3 e to the negative 1.2 plus 50 over 3. Now if we do a little bit of math, we can pull out and we can see this is 50 over 3 times 1 minus e to the negative 1.2. I just move things around a little bit just to make it look a little bit nicer. So now this gives us 50 over 3 times 1 minus 0.301, which is approximately 50 over 3 times 0.699, I believe, which is approximately 11.65. And this would be perhaps whatever concentration, whatever the measurements are. Okay, so we're going to come back into a different video for Riemann sums, and but we've explained the fundamental theorem over here. Good luck, and I will see you in the next video.